Yes. So yeah. So as I was saying, jumping on linear regulators. So today we will cover, as they are, the standard linear regulator, as well as low dropout regulator, which is more known as an LDO, which is, the LDO is just another style of linear regulator. It's just a little more, it's a little, just slight differences, has some advantages, some disadvantages compared to the standard linear regulator. But in their simplest, these are linear voltage regulating devices that function as step-down converters. That is, we have some input voltage, we step it down to some other level to have our output voltage. Because of the design and kind of system of these linear regulators, they can only operate as step-down converters. You'll never be able to boost your V out, so you can only drop from V in, drop down from V in to V out. The standard circuit diagram, you'll see either there's two general different symbols depending if you have fixed or adjustable. So if you have a fixed, you'll just have your V in, the ground, and your V out. For fixed, or you can have an adjustable, which basically same thing, V in, V out, ground, but you also have a feedback pin. So if we jump inside to what these devices actually look like, what we get is your V in, typically an NPN transistor, and your V out. So we'll have, the internals will have a op amp set up in a non-inverting configuration. This is so that we can take advantage of negative feedback loop characteristics that that op amps have. I will discuss the op amp negative feedback non-inverting stuff in another lesson, to actually kind of deep dive onto what that means and how the device actually behaves that way, and what's able to actually, why it's able to do these, why it's able to do this. But simple point to be made about the op amp being used for a negative feedback loop is that the output will change to drive the difference between your two inputs to 0. Does the question so far, just very basic on the op amp, make sense, or do you want a little bit of an explanation further on that?
Probably be helpful to see like how it's negative feedback and how that works around the regulator and how it affects the transistor.
Yeah. So I'll jump into that a little bit, but just very specifically, just any question on the actual negative feedback op amp relation, or does that make enough sense? And we'll leave that for another lesson. Mostly fine. Okay, so to build off of this relation, if we supply, or yeah, so let's say we want this to be 9 volts to 5 volt regulator. So we're going to supply 9 volts on the input, and we want to see 5 volts on the output. What we will see is we have to have a 5 volt reference. So we'll have, initially you can see it as we'll have a 9 volt rail coming in. So there's a difference between our two inputs, 5 volts to 9 volts. So the output wants to change that such that, since we can see our current path is the output ties directly back to the one input pin, the output wants to change such that this pin also drops down to 5 volts, so that our two input pins, the difference between them is 0. And when we achieve this, since this pin is technically connected to our output, we'll see 5 volts on our output, which is desired from our converter.
Wait, how does it change the difference to 0?
That's yeah, so that dives into the operation of a non-inverting op amp, or yes, of a non-inverting op amp with the negative feedback. But what we can see is when we have this setup, the output is of the op amp is controlling the base of our NPM. So what we can do is it can basically send no power out so that the base isn't getting any current. So our device will act as an open switch, allowing no power through. Feeds back, power's decreasing in the system, and then it can basically modulate sending ones and zeros repeatedly. It can modulate. Hold on a second.
What happened?
Sorry.
Is he gone? Oh.
Sorry, there is just noisy people in my house.
Oh, okay.
But we can basically start modulating the base of our transistor to allow and block that power flow, such that we're again. So if we were to take it in a easy state, just assume we were pulsing this gate with a 50% cycle. So we're doing a 50%. We're only allowing 50% of our 9-volt signal. What you can basically see is that you'll have 4.5 volts on that'll be your average DC output coming from that. So if we were just to simple assume that we still had our 5-volt VREF, modulating it perfectly 50%, 4.5 comes to our input, our negative pin, and now it's below, so it's going to increase its duty cycle so that it's on for a little bit longer each time, so that we can allow more power to come through. So it'll continue to do this until it'll continue to do this kind of system until we can see that we'll have 5 volts coming to the base, and then you can have 5 volts on both pins, so the difference between your two inputs is 0, which is the characteristic that it's trying to achieve here.
This is for the linear regulator?
Yes.
I think the negative feedback definitely makes sense, but for the linear ones, they're not switching, right?
Yeah, they're yes, they're not switching. So when I say it this way, this is kind of the theory, like a simplified version, because yes, these aren't switching devices. These are linear devices, so it's always sending something out. It's not switching, pulsing 1 zeros, for sure. Kind of take it as the thought of how it's going is to consider switching. But yes, for sure, it doesn't actually have this pulsing behavior. Instead, it's just sending different levels. yeah, it sends a varying output.
Yeah, so there's different amounts of current to the base of that transistor that like makes it operate as like a variable resistor, right? So the voltage drop across it will be different.
Voltage drop across the op amp.
Across the
Be-
emitter and the collector of the
Oh.
transistor.
Okay.
And
That's why they get hot. But yeah.
yeah, because what we saw from the transistors is that um, your collector current is a ratio of your base current. So your current flowing through the device is proportional to some constant times your base current. So the op amp is able to send varying levels of the base current to modify the current flow, the current that actually flows across the transistor.
Oh, so it's controlling the current. But what about initially though? Like, I'd assume when everything is off, excuse me, when everything is off, the base of the transistor isn't powered. So, where's that input going?
When well, off the bat, so say you haven't plugged this in yet.
Yep.
When you first apply power, because you're also applying power to your op amp, this pin is going to be 0 volts.
Okay.
So again, right off the bat, as soon as you power this device, since you turn on your system, you give power to your op amp, or you give power to your device, you instantly see a difference between your two inputs of 5 volts and 0 volts. So it's already going to want to be controlling the current. It's going to start to try pulling that current to be able to draw.
Oh, I see.
To boost it up so that it can start to see 5 volts on this pin. So yeah, like initially, like it's obviously not going to see your 9 volts right away because you haven't turned it on, you haven't switched it yet. But as soon as your op amp is active, it already sees a difference between your positive pin, which has a steady 5 volt reference, typically internally built into the linear regulator, and your negative pin, which would be sitting at 0 volts or whatever, if there may be something already attached to your output that has some voltage sitting, most likely one. So it would be just sitting at 0. So it wants to already start trying to pull those pins together.
Oh, so it starts at 0, like the negative side of the op amp starts at 0, which still outputs the same, which still outputs like
Yeah.
the op amp outputs to the base, and then which allows the 9 volts, and then another 9 volts is down there, and then it just keeps reducing up to 5.
Yeah,
Which
so
the
it
graph,
basically it'll basically see something of the sort. So initially you have nothing, so it'll send, whatever, large current to try to pull these together. We're acting as we're able to allow some current flow, we're now going to see some voltage, and it's going to realize maybe it's now over 5 volts on this pin. So it's going to decrease the amount that it's letting through. So that it'll decrease the current flowing through the transistor. So this will come down a little bit, and it can have so your actual output voltage can be something of, if that's our desired 5-volt output, it can be something like that, and then it can it'll keep alternating. It'll keep playing with the output, the op amp's output current, until it can finally stabilize the 2 input pins, and we come and sit on a nice 5 volts. Make sense?
Yes, that graph's what I was looking for. Thank you, thank you.
Any other questions on how we achieve, any of this is going on so far?
What exactly is the V reference?
Yeah, so
What's making it?
The V reference is going to be, if you were in the embedded chat, embedded session last week, or whatever week before, Gabe mentioned these special ICs that hold steady values. So you'll input whatever 3.3 volts, and it'll output a nice steady, 1.8 volts to your CPU. This is basically the same thing that's going on inside the linear regulator as well. So what we'll see is, so you'll have your actual linear regulator. You'll have your input pins. Transistor, you'll have an op amp, and then you'll have a separate, just very precise VREF IC that will, it'll take your input voltage, so that gets sent to your VREF to produce some stable voltage, and then it also sends it to the op amp to actually be able to turn on. But yeah, there's a separate chip inside, that's able to have a steady output voltage.
Okay, makes sense.
Any other questions on any build-up so far?
All right, just about the graph. So initially, in one instant, does that mean the output of the linear regulator becomes 9 volts? Like at that one point, at some point in time?
Technically, in an instant, yes. That's why most LDOs in circuits and in the data sheets for these, what you'll see is capacitors on input and output to kind of eat at these ripples. It has the effect of smoothing these out, but we're able to take since that 9 volts and any substantial spikes are going to be instantaneous, like they're going to be a transient high frequency just for a quick second. Boom, it's all of a sudden up at 9 volts. That capacitor is able to kind of eat at that voltage, so we don't send 9 volts to our devices that may only be 5 volt tolerant.
Yeah, that's what I was worried about. Like, what if the devices are just rated at 5 volts? I see. Are those internal resistors or external? Like we have to put them on it.
The caps?
The caps.
They're external. Yeah, maybe if we were to pull up actual sheet, there might be some internal capacitance setup that would do a little bit of the suppression. But in basically every application, you'll see they tell you to put these, and they'll tell you exactly what level of capacitor rating you should be using to efficiently be using this.
I see. Would you by chance know what the waveform would look like with those capacitors there?
I probably drew the with capacitor.
Oh.
What did you just send?
That's the LDO used on the VCU. So on page 2, you would see a sample schematic where you have to put external capacitors.
Yeah, so right off the bat, you'll be told to put these. Yeah, and with that, we're able to see I just randomly went. So you can see the instant we switch on our device, our input is a nice sharp step, but because of all of the capacitance and they're not wanting to change to voltage, we'll have a much slower ramp up before it holds steady at the desired output. Now you would be able to play with these capacitor values. Decreasing them would have a sharper step, so it could potentially look closer. So if you have large caps, your input would be that, and your output would be a much slower, but you would basically never overshoot. Whereas if we have small caps, we would potentially be able to see a much faster curve step up for our output, but also a higher probability that we overshoot. So it's, for most cases, since your devices you're stepping it down to 5 volts for a reason, it's generally because those devices run off of 5 volts and don't like much higher. It is much more, in most applications, it's much more preferred to have the slower response compared to peaks and just short your device. With saying that, even though like we're calling this a slow transition, this happens in what, 10, 20, 30, basically 50 microseconds from switching on to having your output to be to the correct voltage. So it's not like it's drastically going to take 2 seconds before it gets the proper voltage. It is a matter of microseconds, so it's not an awful wait time. Does that make sense?
Yeah.
So yeah, you'll basically always have to put on these external caps for the filtering reasons and transient spike suppressions. Does anybody else have anything on this? Since this is kind of the basic of the linear regulator. No? Okay. So the
Oh, I have a comment. Oftentimes, if you have a large load on your linear regulators, like you're drawing a lot of current from them, the voltage tends to drop. So having external capacitance, even more than the datasheet, can help prop up that voltage and keep it solid.
Yeah, with high current loads, you'll often tend to see what's known as voltage sag. So that is at high currents, your voltage will dip a little bit if you're holding at that high current. So yeah, if we have large external caps, they're able to push back out some voltage to kind of help you out and keep it where you're supposed to be. Now with still on the fixed, this VREF, because again, it's one of these kind of special small voltage kind of constant regulators. They typically don't come in that high of voltage. So what our VREF is typically, it's going to be some 1.1 to maybe 2 volts on the VREF, potentially. Yeah, I think that's the general range. So now all of a sudden we only have, let's just call it 2 volts on our VREF. But we still want to be able to achieve this 9 volts down to 5 volts. Before, we would just tie it straight in, because if the ref was sitting at 5 volts and we're trying to draw the 2 inputs together, then obviously our negative pin is going to want to get up to 5 volts. But if our VREF is only 2 volts, by doing this short, all we're able to achieve is 2 volts, which would be 2 volts on our output, which is undesired. to solve this, if we want to see the 5 volts on the output, what we can do is do a voltage divider before we send it to the pin of whatever ratio is required, such that 5 volts on your output will equal 2 volts on your negative pin. It uses the gain equation from a non-inverting op amp, so it's not as simple as what you would just suspect. Whatever your standard voltage divider is. Instead, there's data sheets will give you a separate equation based on whatever resistor values need to be. That's not those. But at the moment, we don't care because, again, this is all internal to the device. So these resistors, we don't have to pick out. We don't have to do anything with them. These are already inside the device. They're perfectly spec'd out so that they can achieve this, so that we can still see a 5 volt output while only having a much smaller reference voltage. Yeah, but the logic still follows exactly the same. We just have to do a small voltage drop to be able to talk the same as our reference voltage. That makes sense to everyone? Just because we're never, it's very typical that our reference voltage internally is always going to be some 1 point to 2 point something voltage range. So if we want to be able to achieve something like 5 volts or even higher, there needs to be some gain built in.
Okay, I'm gonna ask another question.
Good.
I wasn't listening. Why is it only 1.1 to 2 volts? Why can't it just be 5 volts or something?
Because that's just a manufacturing kind of restriction. It's much easier to produce reference voltage chips that are 0.8 to 2 volts. That's much easier to make compared to 5 volt plus devices. So you'll basically always just see devices will use some reference chip of a much lower value.
Gotcha. Okay.
Yeah. Any other questions so far on any of this? To all you that are being quiet. Makes sense so far? then we can slide directly into the adjustable linear regulator, which is no different than what we just saw. We'll have whatever Vref, again call it 2 volts, and this time, so that's your V out, and that's your feedback pin. So external to the device, you place these resistors. And that's your now V out. So the adjustable is no different to what a linear regulator truly looks like, because a true one will have these internal resistors because of this restriction. So in an adjustable, we are not just stuck with, okay, we got a 9 to 5, we have to deal with it. We're now able to change these resistors ourselves, so that maybe we're able to achieve 6 volts, 5 volts, 4 volts. Most data sheets will give you a little table saying use these resistors to achieve this output voltage. So we're able to, with an adjustable linear regulator, we choose the resistors that are tied to this and that are tied to the feedback pin, so that the range is at our control now. Yeah, so the difference will be minimal between the two. The one we just have the control, and again, it's not as straightforward as doing the voltage divider, because op amps work in a slightly different manner. The non-inverting op amp has a separate gain equation associated with it to be able to drive the outputs to the same. And the data sheets will tell you exactly what you need to be able to put, to be able to, like, what resistor values are needed to be able to actually drive that output. But your standard gain equation is just going to be R2R over 1 plus 1. That's your gain. So whatever your input times gain will be your output. So in this case, input is your feedback pin. Output is what goes to the base. So we can see that it's not as straightforward as just know your internal reference, know your voltage divider, have an output. But again, data sheets give you this equation, so you don't have to derive anything or actually properly know what your reference voltages are or anything like that. questions on the adjustable? All make sense? Now, in most applications for your standard linear regulator, the transistor used will be in the Darlington pair, which covered at the end of the transistor session, whatever, 2 weeks ago now. This is so that we're able to allow more current flow through the device. It can handle more power compared to just using a standard, just single transistor. The downside to the Darlington pair that we saw last time is your voltage drop increases. So that being from your standard whatever 0.7 to 1 volt, we will now see voltage drops of 1.2 to potentially 2.5 volts as the voltage drop across our transistor. The problem or the side effect to this is if we have a 2-volt drop across our transistor, in no case are we able to take 9 volts and spit out 8 volts. Because we always will lose 2 volts across our system, we maximum can only output 7 volts on our device because of the drop. We're not able to have output and input be too tightly together. This is it's more commonly seen or matters more when we have more practical systems of we have 5-volt inputs and we are wanting, say, 3.3. Since this is a more common, what a microcontroller is able to produce, or that's a very typical supply on the boards, and you want to be able to drop it to 3.3 to be able to work within most microcontroller pins. Again, if we have a 2-volt drop, we're not able to achieve this 5 to 3.3. And there becomes the problem of not being able to get that range. This is where the LDO comes in. Again, it's a low dropout. So what an LDO essentially runs the same. It'll run the same setup, vref, internal, external resistors, whatever the device actually is. But we'll more commonly have a PNP transistor. Did I draw that right? I'll say I did. Which in most cases produces a lower voltage drop. Being much finer, 0.4 to like 1 volts, I believe, is more of the expected range. So now all of a sudden, by switching from a linear regulator down to an LDO, with the major difference primarily being a switch in the transistor, we are now able to achieve these 5 volts to 3.3 volts regulators without concern of cutoff and not being able to get our full range on the output. Questions on anything so far? Voltage drops, why we use LDO versus standard linear. Nothing, no one? If LDOs are much nicer, they don't have such a large voltage drop, why don't we use LDOs more compared to the normal linear regulator? Can anybody hazard a guess?
Is it something related to the load having to be is it after the thing? Oh, I'm not really sure.
Yeah, no, there's it's fine with being this high side power delivery device. So it's okay with it's not so much a matter of, you know, the high side versus low side, like we were talking about in the transistor system. But there's the more inherent stability problems, and lower current outputs, typically. Again, because it's not running the Darlington pair, or even if it is running a PNP Darlington, the output current, the output power from that will be lower compared to that of the NPN counterpart. So we can see we won't be able to see as high of currents flowing through our device, and there apparently is some inherent stability problems when using a PNP. I don't know fully the effects of such problems, but from research, apparently there is problems associated with the with having the PNP. Any questions, I guess, general so far, or before we come close to ending? Okay. Okay. Question, or someone have something?
Can I bug you again?
Oh,
um,
please.
for the Darlington pair, not the low dropout one, the one above it,
The standard.
the standard one, yes. Don't we want? Isn't that good? Isn't that voltage drop good? So we get a lower transient response.
Yes, in most applications it is. It helps suppress um, alongside your externals.
Mhm.
So yeah, in normal it is beneficial, or it isn't detrimental that there is a voltage drop. Only when you're really trying to accomplish um, these fine step downs does it become a hindrance.
Oh, so what we call it? This linear voltage regulator. This is more used for powering, like different sources of power. And whilst the other one is for powering pins. Is that like pins in a microcontroller?
Uh,
Is that
both, either can do
making?
both, because we could, in just this normal linear, we can give it, your 12-volt supply and bring it all the way down to 3.3 volts. There's no problem with that.
Mhm.
Uh, and the same thing can be done with an LDO. You're able to give it 12 volts and still get that 3.3. Like, they're both able to accomplish big step downs like this. But where you start to distinguish becomes more in the finer drops. So if you only have 5 volts coming into your board, and you need to be able to power pins, or send to microcontroller pins, then you're going to need to be able to hit that finer step down to be able to hit the okay value of 3.3. But I mean, depending on full system parameters and everything, you technically could use either a standard linear regulator or an LDO for doing 12 volts to 3.3 volts.
So, in my head, this is how I understand the application wise. The LDO is more used for low step downs then, as opposed to the other one is more efficient and higher current, more stable in general. So you'd use that generally.
Yeah, exactly. Is there anything else? Koye, you were about to speak up, weren't you?
Yeah, like have we talked about DC-DC converter yet, or just
No, I was gonna do this in the same, but I figured this one would already take an hour or so. Next week we'll talk about switching regulators, so buck and boost.
Okay.
But yeah, so that's next.
Yeah. Yeah, but is there any like really concern about like high voltage applications? Because like the one that we use, like, I don't know, like because like for high voltage, like for the battery or something like that, you could really use high voltage, right?
Yeah, so there are linear regulators that are able to take, 200 volts and bring it down to, 5 volts. Those are available. This is where we start to compare these linear voltage regulating device compared to switching voltage regulator devices. And while it is possible, it's a matter of efficiency. Because as you can imagine, say this is spec'd out properly, it's able to handle such high power. And we're trying to get that stable 5 volts. That is constantly being, well, just in general, linear regulators, you're constantly just always powering this device. You're always feeding it power. It's always running through the system. So you'll have a lot of heat losses and power dissipation because to go from 200 down to 5, that power has to go somewhere. So, in the resistors that actually step it down, and just in general through the system, you'll have a lot of power losses due to heat. So this starts to become a lot less efficient, purely because you just start burning through power, because got to go somewhere to be able to drop 200 down to 5. Anything else?
Yeah. So for linear regulator, like between a DC-DC and a linear regulator, they're both going to have those feedback resistors and comparison networks. But where the real power gets dropped is across that transistor, right? So in a linear regulator, the golden rule is current in equals current out. So if you have 5 amps coming in to the input, then that passes through the transistor and you have 5 amps coming out of it as well in that main current path. So you can imagine if you have 5 amps coming in and you have a 195 volt drop across that transistor, then that's a huge power loss, right? Power is voltage times current, so 5 amps times 195 volts.
Is whatever that math turns out to be.
What is that, 475? No, sorry.
No, much higher.
970?
Nearly 1,000. Yeah, that's nearly 1,000 watts.
That's 1,000 watts. Right? That's where your energy is going, and it's burning across that transistor, which is basically acting as a variable resistor. And so because of this current in, current out rule, we lose a lot of energy. And the general thing we kind of look at is what's the power at the input? So that would be 200 times 5 amps is the input power, right? So that's your full 1,000. Yeah. Then your power at the output is 5 amps times 5 volts, which is 25 watts. And so all of a sudden, if I buy a 1,000-watt power supply and I'm putting it in here, I've lost 975 watts of power, right? And you're only getting 25 watts out. So that's the downside to linear regulators. And you can imagine the more higher current you're passing through, the more energy you're losing because of this current in, current out rule. And that little transistor bears the brunt of all of this power loss. And so it gets really hot and the resistance goes up. And so these linear regulators and LDOs are not meant for high current supplies because they're going to get rid of all your energy and overheat, which is why people invented the DC-DC, which Jared will talk about next week. And the cool thing about those is roughly power in equals power out. So if I put in 1,000 watts from my power supply, I get out really close to 1,000 watts, probably about 900 watts I'd get out, because there's a little bit of inefficiency, but it's much better for actually not wasting your energy.
Yeah. So I mean, Coy and Braden, both you would have seen this in the high voltage board and the T-cell AIL. That is why you guys really only have 10 milliamps on your output, that you hardly have enough to light an LED. It's because they're trying to negate these losses, only allow. So by pushing such a small current, you can reduce that power draw. So that's why in your guys' systems you'll only have 10 milliamps worth, knowing when you're trying to properly looking at it in this power system. That is everything I had on linear voltage regulators. So, final questions before we just move over into the meeting? LDOs versus switching. Well, I'll take no comments as you just don't want to say anything, but we'll move on anyways. Okay, so we can shift over to